This is the second lecture on the iron carbon system, focusing specifically on isothermal transformation. So if you haven't watched the first lecture, do that first before you jump into this one. Um, so remember we had developed this diagram previously, but I want to remind you that an isothermal diagram is effectively representing an instantaneous change in temperature and holding at a fixed temperature. So we don't really have a continuous change in temperature. We change it to whatever we want and then we just hold it there. What that basically means is that we can only move vertically down or horizontally to the right on this curve. So, and any sort of diagonal lines that we see going backwards uh, are just representing an instantaneous change in temperature again, and then resetting the time. So, for example, if we were to say let cool down from above the eutectoid transformation temperature of 727 down to, let's say, 500 degrees, and then we would hold for, in this case, it looks like about a couple hundred seconds. Uh, the question then would remain, and then we cooled it down to, let's say, room temperature. What sort of a microstructure do we have? Well, in this case, we have converted at the 500 degree temperature. We had converted all of the austenite into 100% bainite. So remember too that this diagram is primarily showing you the transformation of austenite into either perlite, bainite, or martensite. Right on this graph, I'm not showing you martensite, but obviously it's there. What that means is that when I cool down from the bainite to room temperature, even though I go back through this red curve, back through even the green curve, it doesn't do anything to the microstructure because I don't have any more austenite remaining. And so at the end of cooling down, I still have 100% bainite. It will be my microstructure. Okay. So now let's go ahead and we're going to work through several examples to show you how these diagrams work. So I want to try to produce 4 different microstructures. The first is a 100% coarse perlite. Remember, we form coarse perlite by cooling relatively close to the eutectoid temperature, as opposed to fine perlite, which is where we cool it further from the eutectoid temperature. Uh, for part B, we want to see how could we create a 50-50 microstructure of fine perlite and bainite. For part C, we want to show how to create 100% martensite. And for part D, we want to talk about how to do a 50% austenite, 50% martensite microstructure. So let's do part A. We want to create 100% coarse perlite. Well, to do that, we're going to need to cool it to some temperature that is, so we said coarse perlite forms close to the eutectoid. Fine perlite is going to form in these temperatures over here. So let's go ahead and cool to, let's say, 650 degrees C. So there we go. We cool to 650 degrees C. And now we want to hold for an appropriate length of time. So an appropriate length to form 100% perlite is just any length of time that gets us past this green curve, because that's the 100% transformation line. So we hold to, in this case, looks like about 2,000 seconds, and then we can go ahead and cool to room temperature if we want. That will give us 100% coarse perlite. Okay, now let's move on to the 50% fine perlite, 50% bainite case. So remember, fine perlite forms much closer to this nose, further away from the eutectoid transformation temperature. So in this case, let's cool down to, let's say, 550 degrees C. So, and then we're going to hold. We want to create 50% fine perlite. So we want to hold right until we get to this 50% transformation line. So that looks to be, let's say 3 seconds or something. So we hold at that temperature for 3 seconds. Now we want to take the remaining austenite and convert it to bainite. That means we have to rapid cool to, let's say, 500 degrees and then completely transform the remaining austenite to bainite. So if we do that, we rapidly cool back to 500 degrees and reset the time, and then we cool over so that we hold long enough, in this case 10 seconds, so that the remaining austenite gets converted to 100% bainite, and we end up with then a 50-50 microstructure of fine perlite and 50% bainite. Okay, that was the hardest one. Now the 100% Martensite is very easy. We just need to rapid cool uh, down to some temperature, probably room temperature, over a very short period of time, considerably less than 1 second. That will give us 100% Martensite. The reason I chose an example of 50% austenite and 50% martensite is because it illustrates an important feature of martensite, which is that once it forms, it only matters what the temperature is. It doesn't matter how long it's there for. So if we want to form a 50-50 austenite martensite microstructure, we have to cool it to the 50% martensite line, which exists, I don't know, about, let's say 170, 75 degrees C, and we have to hold there indefinitely. So if you want that microstructure, it only exists at 175 degrees C out to infinity. If we cooled it down to room temperature at any time, we would just finish the conversion of martensite, or sorry, finish the conversion of austenite into more martensite. So those are sort of kind of the four representative example problems of how to use this time temperature transformation diagram. I want to also remind you that this diagram is relevant this particular diagram was created for a composition that was equal to the eutectoid composition, so 0.76 weight percent carbon. It's possible to look at a time temperature transformation diagram that is away from the eutectoid composition. So what I'm showing you here is actually coming from your textbook. Now we have a carbon composition of 1.13 weight percent carbon. That's just by definition. That's how this time temperature transformation curve came about. We want to do another example here. What's the microstructure that's produced by rapidly cooling to 600 degrees C? So there we go, from the austenite, and holding for 10 seconds. So there we go, we hold for 10 seconds. We want to ask the question, so we want the microstructure, and then we want to know the fraction of pro-eutectoid cementite to perlite, because we also know that we're above the eutectoid composition, so we expect to see pro-eutectoid cementite forming. In fact, that is what the C here represents, is that pro-eutectoid cementite. So when does that happen? Well, the pro-eutectoid cementite forms in this region here, and which means that the microstructure that we have remaining is some combination of perlite, where the remaining austenite was converted to perlite, plus the pro-eutectoid cementite that had formed before we had transformed the austenite. Okay, so that's what the microstructure is. That doesn't tell us yet how much of each. So we want to ask that question, and then this actually is an easier answer than it seems. To solve this, we just go back to our lever rule. So the amount of each phase is still determined from our phase diagram, so we use the lever rule. So let's go ahead. Remember, we're at a composition of 1.13 weight percent carbon. So we locate that on our phase diagram. We draw a tie line just like we've done before. Right before at that temperature, right before that eutectoid temperature, we compute what the weight the weight of the phase amount of the pro-eutectoid cementite is, and we do that with the lever rule. So we compute that as 1.13, this value here, minus 0.76 divided by 6.7 minus 0.76. We find out that there's about 6.2% of pro-eutectoid cementite in the microstructure, which means that the remaining austenite is getting converted to perlite in this case, and so we would have a weight fraction of perlite of 0.938. So hopefully that was pretty straightforward. Okay, now let's go ahead and I know this is a lecture about isothermal phase transformations, but I at least want to make you aware of the fact that there are also continuous cooling phase diagrams, because sometimes we just can't, it's not realistic to think that we could cool instantaneously, and then holding isothermally is not so hard. Oftentimes we will be able to cool at a fixed rate. So if we use a fixed rate instead of a rapid cool and hold, then we end up with what's called a continuous cooling transformation diagram. And the main feature here is that each curve now, so you have the same shape, an austenite to perlite region that we had before. It's worth noting that bainite doesn't usually form in a continuous cooling case because we can't cool it fast enough in that fashion. And so we really only have three possible um, three possible phases. We have martensite, we have perlite, and we have austenite. There's no bainite here. So what happens is that if we cool any curve that would take us, so this is showing you 140 degrees C cooling rate, this is 35 degrees C cooling rate. Any curve that would take us through this dashed line, uh, that's going to basically stop the reaction going from austenite to perlite, and it's going to just go from austenite to martensite. So that's it. I just want to make you aware that that exists. If you have an application where this is needed, then this is the diagram that you would use. Okay, finishing up sort of the discussion about transformations, I want to mention briefly what's the effect of alloying, and this is showing you the effect of alloying on the eutectoid temperature. So various alloying elements with your steel, so titanium, molybdenum, silicon, tungsten, chromium, manganese, nickel, etc. All the weight percent of the alloy with the steel changes the eutectoid temperature, and it changes the eutectoid composition. So remember here with no alloying elements, we have a eutectoid temperature of 727 C. So we can alloy it to change that temperature. And remember here, this was uh, eutectoid composition of 0.76 weight percent carbon. And you can see everything changes from there. In this case, all the alloying elements reduce the eutectoid composition in the steel. So just be aware that if you alloy it, it does change these values on your phase diagram. Similarly, alloying will affect your time temperature transformation diagrams. And what I'm showing you on the left here is a isothermal time temperature transformation diagram, and you can see that it changes the shape fairly substantially over what we had in the non-alloyed case. And then on the right, I'm showing you the continuously cooled transformation diagram for an alloy steel. I think this one is 4340 steel. So that sort of concludes the discussion on iron carbon phase transformations. We're going to start moving to talk now that we know all about these phase transformations, how can we use that to do thermal processing of steels to create the kind of properties that we want out of our steel alloys.